Welcome everyone, thank you for being here. Today I will try to show you that computational engineering can become a serious competitive advantage in the comminution industry. Today I would like to present you my master thesis about the discrete element method modeling of ball mills, and in particular about the liner wear evolution. So let's delve into the topic by a short video. Today we will talk about the ball mill. We will also talk about the discrete element method simulation of the grinding charge. And finally, we will talk about the liner wear. This means the change in the geometry of the liner plates due to the collisions with the metal balls. As I just said, I got essentially three things I would like to talk with you about today: the ball mill, the discrete element method, and the wear simulation. But there's also one more thing I would like to show you, and this is why I would present you one further application of the simulation method, which was not presented in the master thesis. To recap, ball mills are used to grind the feed material like the clinker in the cement industry in order to enhance its chemical and physical properties by increasing its surface to volume ratio. Ball milling is, however, not only highly energy intensive, but also very aggressive in terms of wear. For this reason, a profiled and wear-resistant liner enhances the energy transfer from the mill to the grinding charge, and it protects the mill shell, so the outer part of the mill, at the same time. Therefore, the operational performance of the mill depends not only on its operating conditions, like the filling ratio and the rotation speed, but also on the liner itself. For this reason, the slightest improvement of the liner design can become a serious competitive advantage. The objective of this thesis is therefore to develop a method which is able to predict the motion of the bolts inside of the mill, as well as its power draw on the one hand. On the other hand, we want to predict the wear. This means the change in the shape of the liner plates due to the collisions with the metal balls. The most promising simulation method to reach these objectives is the discrete element method. This method, which is also known as DEM or DEM, is based on three fundamental components: bodies, interactions, and the time integration. So in the case of a ball mill, the bodies are essentially spherical elements representing the bolts, and triangular facets or surface meshes representing the liner. So while these facets are rotating around the rotation axis of the mill, the bolts are floating in space according to Newton's second law. In order to prevent these bolts from overlapping completely when they collide, their contacts have to be detected by a collision detection algorithm, which is the most computationally intensive part of the simulation. So once these contacts are known, the absolute overlap and the overlapping velocities are transformed into a normal and a tangential collision force, which is applied to both bodies on basis of the linear spring slider damper contact law, which is just shown here. Finally, the explicit leapfrog time integration scheme renders it possible to determine the position of the bolts at the following time step. But since the forces are known, the accelerations can be determined by Newton's second law. Once these accelerations are known, the velocities are calculated by this algorithm, and once the velocities are known, the positions at the following time steps are known. So now we talked about the ball mill, and we also talked about the discrete element method. Hence, the question rises whether this method is actually able to simulate the motion of the bolts inside of the mill. To calibrate and validate the discrete element method results, Magato kindly provided me with some charge motion photographs and power draw measurements taken in an 0.8 meter diameter laboratory mill. Moreover, I implemented the linear spring slider damper contact law in Yate, which is a very versatile, open source discrete element method solver. So finally, after an extensive calibration and validation phase, an extraordinary correlation between the theory and the reality was obtained. So let's take a look at it. So the color code in this video represents the translation velocity of the bolts. So now I will superimpose a picture of the laboratory mill. And the correlation is quite good. So besides this charge motion, the correlation is also very good for the power draw, since the error between the predicted power draw and the real power draw remains below 5%, which means that the power can also be predicted. So now we know what a ball mill is, but we also know that the discrete element method can simulate the motion of the balls with confidence. The next step is therefore to determine the wear of the liner plates. This means the change in their shape over time due to the collisions with the metal balls. In the same way as for the validation of the discrete element method, I started with some experimental data, which was again kindly provided by Makoto. This data essentially consists of the wear profiles of a liner plate in a 5.8 meter diameter cement tube mill. A tube mill is basically a long ball mill. Interestingly, the geometry of the liner changes not only along the azimuthal direction, but it also changes along the axial direction, which means that grooves are created. This is just shown here. To predict this change in the geometry, a wear model is required. This model translates kinematic, dynamic, or energetic data, like for instance the tangential damping energy, into an equivalent volume loss. For this reason, a charge motion simulation is also required. And what a chance! This is actually what we did before. Hence we can use the discrete element method to record this wear data. The real mill, or at least the first chamber of the tube mill, contains however about 100,000 balls. And this number of elements would require several days of computation time. Therefore, only an axial slice of 0.25 meters was simulated with frictionless end walls in order to prevent the balls from leaving the mill and without inducing any tangential interaction. Finally, the wear data has to be accumulated on a binning structure. So in simple words, each facet has to know which is its wear level. Therefore, I considered two different binning structures, which I call a coarse 1D mesh and a fine 2D mesh. So while the 1D mesh is only able to capture the wear distribution along the azimuthal direction, the 2D mesh is also able to capture this variation along the axial direction. So now we have some experimental data, and we also have a charge motion model. This means that we are ready for the wear simulation in 7 steps. First, we have to reach the pseudo-steady state to accumulate the wear data, since real ball mills rotate at a constant angular speed during several 10,000 hours. So initially, the charge is lifted up, then it falls down, and finally, we are in the pseudo-steady state. Once we have reached this steady state, the wear data for 6 different wear models, like the tangential damping energy, is accumulated for each facet. Moreover, we take advantage of the azimuthal periodicity by mapping all the data on one master plate, which increases the statistical representativity of the data. At the same time, we have extracted the real wear data from the wear profiles by projecting the initial mesh of the plate onto the mesh of a later wear profile. For this reason, we know the real wear rates. This means the volume loss per time of each facet of the initial mesh. So this is just shown here. So at present, we know the real wear and the predicted relative wear, which we determined just 2 slides ago. In order to determine which of the 6 different wear models is the best fitting wear model, we can correlate them. So this is shown here for the tangential damping energy, one of the 6 different wear models, represented by the blue curve. More precisely, this figure shows the wear rate for each axial stripe of the liner mesh along this liner plate. So for this reason, this peak here corresponds to the leading edge of the big wave of the profile. Due to the relatively good correlation between this real wear and the predicted wear, the tangential damping energy is actually the best fitting wear model. And we also determined its wear constant. So for this reason, we can now determine the volume loss of each facet by the simulation. And if we know this volume loss, the next logical step is to modify the geometry in order to take into account this volume loss below each facet. This is why the surface is displaced normally to itself by an amount which is proportional to the predicted volume loss of the respective facets. So let's take a look at the modification of the geometry. So the color code represents the local wear rates. And the problem is obviously that the colors in this video do not change, even though they represent the wear distribution. However, in the real ball mill, the wear distribution changes with the modification of the liner shape due to the modified flow pattern of the bolts. In order to capture this effect in the simulation, the previous steps of the wear simulation have to be repeated, and the geometry has to be adapted by increments. So first the pseudo-steady state has to be reached, then the wear data has to be recorded, and then the geometry has to be modified. Afterwards, the pseudo-steady state has to be reached with the modified geometry, then the wear data has to be accumulated with the updated geometry, and finally the updated geometry has to be updated, and so on. In order to not have always to start from the beginning with the bolts at rest, which have to be lifted up, which fall down, and so on, we simply use the final state of the bolts in the previous simulation as their initial state in the following simulation. That way, the initial state of the bolts is already closer to their second pseudo-steady state. So once this second pseudo-steady state has been reached with the updated mesh, the wear data is again recorded and the geometry updated, and so on. So this procedure is called a multi-step procedure. The results are shown in this animation. So notice how the wear distribution changes over time for the 1D mesh. This wasn't true before. So notice also how the grooves are created for the 2D mesh, which is also the case in the reality. So now we know how works the wear simulation in 7 steps. And maybe you might be wondering if the predicted results are realistic. So therefore this slide shows the linear wear evolution. The solid line is the predicted wear profile and the dashed line the real wear profile. So for the 1D mesh, the prediction is quite accurate, at least until half of the lifespan, and then the gap increases slightly. This might actually be explained by the fact that the real ball mill in which the measurements were taken is one of the few mills with a variable rotation speed. And it seems reasonable that the cement producer increased the rotation speed at this particular moment to keep the mill throughput constant despite the increasingly worn out liner. Other reasons could, however, also explain this gap, like a different clinker quality, a slightly increased filling ratio, and so on. For the 2D mesh, the differences are, however, a little greater, which might be explained by the fact that the wear constant was determined with the 1D mesh. The 2D mesh is, however, able to adapt better to the flow pattern of the bolts and is therefore less worn. Indirectly, this obviously means that the liner design with initial grooves might increase the lifespan of the liner. Further numerical validation studies are, however, still required to assess this conclusion thoroughly. In the thesis, this validation was unfortunately limited by the important computation time. It is, however, possible to validate these results in the near future. So finally, I want you to know that I tried to develop a method which is as general as possible. And to illustrate this versatility, well, let's take a look at one further application, which is the VSI, also known as the vertical shaft impactor mill or the MAC impact. So this device is used to crush rocks. On the picture you can see these yellow parts which are called impellers. These impellers are attached to a table which rotates at about 1,000 rotations per minute around the vertical axis. The rocks which fall onto this table are ejected by the impellers against the peripheral anvils and they are simply crushed. So now I will use exactly the same simulation method than before with the same wear constant and so on in order to predict the wear of the impellers. The advantage of the VSI is obviously that less elements are required than in a ball mill where I have several 10,000 bolts, and therefore the simulation takes less time. So let's take a look at the results. So here you can see that I use a more complex particle shape, so some clumps, and you can also see that the colors represent the local wear rates. These results are actually quite realistic, but they still require some more fine-tuning and calibration, which is possible in the near future. So in conclusion, I will come back to one of the first sentences of this presentation, which was that I would try to show you that computational engineering can become a serious competitive advantage in the comminution industry. And I hope to have convinced you that the methods in this thesis can become powerful tools in the development of better liners and better comminution devices. So thank you for listening. Questions, suggestions and criticism are welcome. Thank you.